December 3rd, 1944. Hürtgen Forest, Germany. Temperature -4 degrees Celsius. Sergeant William McBride's Sherman tank, serial number 3042789, took an 88mm round through the frontal glacis at 09:15 hours. The German shell penetrated 3 inches of American armor plate, travelled through the crew compartment, and exited through the engine deck. 5 men died before the tank rolled to a stop against a shattered pine tree. 30 meters away, Corporal James Rothery watched the familiar pattern of smoke and fire that marked another crew's war ending in the German forest. His own Sherman carried something the manual hadn't authorized. Welded to the frontal hull sat 6 inches of salvaged German armor plate, scavenged from a destroyed Panther tank 3 weeks earlier. The modification violated field maintenance regulations. It added unauthorized weight. It required no official approval because Rothery had never asked for any. By January 1945, 63% of Sherman tanks in the European theatre carried similar unauthorized armor modifications. Crews were welding track sections, concrete, sandbags, and salvaged enemy armor to their vehicles in direct violation of Army technical manuals. Engineering officers called it dangerous. Logistics officers called it wasteful, the crews called it staying alive, and the statistics would prove them absolutely correct. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics of Sherman tank vulnerability were established through brutal experience across 2 years of European combat. Between June 6, 1944 and May 8, 1945, American forces lost 4,295 Sherman tanks to direct enemy fire. An additional 3,127 were damaged severely enough to require depot-level repairs. The casualty rate meant that statistically, every Sherman tank in the European theatre was destroyed or severely damaged approximately 1.7 times during the 11 months of combat operations. 3rd Armoured Division maintained detailed loss records that revealed the grim patterns. Of 232 Sherman casualties between D-Day and the end of August 1944, 147 resulted from German anti-tank gunfire, 62 from Panzerfaust handheld weapons, and 23 from mines or other causes. The critical detail appeared in ballistic analysis reports. 89% of fatal penetrations occurred in the frontal arc, where Sherman armor was supposedly thickest. The problem wasn't armor thickness in absolute terms. Sherman frontal glacis plates measured 51 mm at 47 degrees from vertical, providing approximately 63 mm of effective thickness. Against German 75 mm guns, at typical combat ranges of 800 to 1,000 meters, this protection proved adequate. But against German 88 mm anti-tank guns, the standard weapon in defensive positions throughout occupied Europe, Sherman frontal armor was decisively insufficient. Ordnance Department testing at Aberdeen Proving Ground had established the penetration characteristics with clinical precision. A German 88 mm Pzedgruer 39 armor-piercing round could defeat 63 mm of face-hardened armor at ranges exceeding 1,500 meters. The Sherman's frontal protection, advertised as proof against standard German anti-tank weapons, was obsolete against guns that had been standard Wehrmacht equipment since 1943. Lieutenant Colonel William Stokes of 2nd Armoured Division understood these numbers in ways that ballistic charts never captured. He had watched 37 Shermans under his command burn during the Normandy campaign. Each loss followed identical patterns. German anti-tank gun opens fire from concealed position. Shell penetrates Sherman frontal armor. Ammunition or fuel ignites. Crew has approximately 45 seconds to evacuate before internal temperature exceeds survivable limits. The soldiers called Shermans Ronsons after the cigarette lighter company's advertising slogan, "Lights first time, every time." The gallows humor masked genuine terror. Sherman crews knew their survival depended more on German marksmanship and luck than on American armor protection. Every combat engagement represented a mathematical calculation. How many hits could your tank absorb before the fatal penetration arrived? The answer, according to Third Army statistics, was approximately 1.3 hits per Sherman loss. Crews rarely survived long enough to learn from experience. Corporal James Rothery had joined 3rd Armoured Division as a replacement driver in September 1944, arriving at the front 3 weeks after the division had crossed into Germany. At 23, the former mechanic from Pennsylvania coal country understood machinery in ways that Army training manuals never captured. Before the war, he had kept mining equipment running through combination of technical knowledge and practical improvisation. When company regulations said equipment couldn't be modified, miners welded whatever would keep machinery functioning. His first combat action occurred during the attack on the Siegfried Line fortifications near Aachen. The briefing had been straightforward. German defensive positions included anti-tank guns positioned in concrete bunkers with interlocking fields of fire. Sherman tanks would provide mobile fire support, while infantry cleared fortifications. Acceptable losses were estimated at 15% of attacking armor. The mathematics suggested that statistically, Rothery's crew had 85% chance of surviving the day. The reality proved less optimistic. The attack commenced at 0600 hours with artillery preparation that lasted 45 minutes. Rothery's Sherman advanced with A Company's lead platoon, crossing the line of departure exactly on schedule. German response began at 0652 when concealed 88mm guns opened fire from bunkers that artillery had failed to suppress. The first Sherman died at 700 meters range, the second at 620 meters. Rothery's tank, third in the assault line, suddenly found itself leading the attack. His driver's vision was limited to narrow periscope views that showed cratered ground, burning vehicles, and smoke that reduced visibility to less than 100 meters. The intercom carried tense fragments of radio traffic. Baker, 1-6, is hit. Can't see the gun position. Move forward. Maintain formation. The commands felt surreal, against the metallic impacts of German shells striking nearby ground or glancing off other tanks' armor. At 530 meters, Rothery saw the muzzle flash that meant his crew's war might end in the next 2 seconds. The 88mm round struck the Sherman's frontal glacis, 3 inches left of center. The impact sounded like a massive sledgehammer blow against steel. The shell penetrated the outer armor plate, but the crew compartment remained intact. Rothery's ears rang from concussion, his vision blurred from shock. But he was alive, and the tank was still mobile. Post-battle inspection revealed why. The German shell had struck a section of hull where a previous crew had welded a salvaged piece of track. The improvised armor had distributed the impact energy across a wider area, preventing complete penetration. The factory armor beneath showed severe deformation, but the crew compartment had not been breached. 5 tons of unauthorized modification had saved 5 lives. That evening, Rothery walked through 3rd Armoured's maintenance area, studying other Shermans in various states of repair. Perhaps 40% carried similar modifications. Some crews had welded spare track sections to frontal hulls. Others had attached sandbags filled with dirt. A few tanks carried concrete applied in rough layers over factory armor. The modifications violated technical manual specifications, but they represented practical solutions developed by men who understood that regulations mattered less than survival. The engineering logic was straightforward. Sherman armor could not be made thicker without redesigning the entire vehicle, but additional layers welded to existing armor could distribute impact energy, cause premature detonation of shaped charge warheads, or provide sufficient additional protection to defeat marginal penetrations. The modifications added weight, reduced mechanical reliability, and created maintenance complications. They also kept crews alive long enough to gain combat experience that training could never provide. Rothery's background in mining equipment maintenance provided perspective that West Point engineering courses never taught. When machinery failed underground, solutions used whatever materials were available. Proper parts, official procedures, and approved modifications were luxuries. What mattered was keeping equipment functional, using available resources and practical knowledge. The same principle applied to tanks facing German 88mm guns. Standing in the December cold, watching maintenance crews repair battle damage under portable lights, Rothery made his decision. His Sherman would carry the maximum protective modification that mobility and mechanical systems could tolerate. If regulations prohibited such changes, he simply wouldn't request permission. If engineering officers objected, he would install modifications during off-duty hours. The arithmetic was simple. Additional armor meant additional survival probability. Everything else was secondary. The German steel he needed was readily available. Wehrmacht positions throughout the Siegfried Line contained destroyed or abandoned tanks that Allied forces had already bypassed. Panther and Tiger tanks carried frontal armor measuring 80 to 100 mm in thickness, far superior to Sherman protection. The German vehicles had been destroyed by overwhelming numbers, air attacks, or mechanical failure rather than inadequate armor. Their hulls represented premium raw material, properly hardened, correctly specified, waiting to be repurposed for American use. Within the maintenance culture of American armored divisions, unauthorized modifications occupied an ambiguous status. Technical manuals specified exact procedures for equipment repair and maintenance. Modifications required approval through proper engineering channels, extensive testing, and formal authorization that typically took months to process. The system had been designed by peacetime military bureaucracy that valued procedure and documentation over battlefield adaptability. Combat reality operated under different rules. Tank commanders needed solutions measured in hours, not months. Crews facing German anti-tank guns tomorrow couldn't wait for Aberdeen Proving Ground to complete ballistic testing and issue formal modification authorizations. Battlefield problems required battlefield solutions, implemented with available materials and crew initiative. The unspoken agreement between field officers and maintenance personnel acknowledged this reality. Officers who wanted their units to survive learned not to ask too many questions about unauthorized modifications. Maintenance sergeants who understood combat requirements developed selective attention toward regulatory violations that improved crew survivability. The system worked because everyone understood that inflexible adherence to peacetime procedures meant unnecessary casualties. Rothery began collecting materials 2 days after his near-fatal encounter with the German 88mm gun. A destroyed Panther tank sat 300 meters behind American lines, its hull relatively intact despite the catastrophic turret penetration that had killed its crew. The frontal glacis plate measured 80 millimeters thick, properly hardened, excellent quality German armor steel that had been forged in the Ruhr Valley and machined to precise specifications. Cutting the plate required acetylene torches borrowed from the Division Engineer Battalion. The work took 8 hours, performed during a rest day when the division was pulled back for maintenance and resupply. Rothery worked with 2 other crew members, cutting sections approximately 2 feet square that could be positioned over the Sherman's most vulnerable areas. The German steel weighed approximately 45 pounds per square foot, making transportation and installation physically demanding. Installation required both welding equipment and careful planning. The German armor had to be positioned to provide maximum protection without interfering with vision blocks, weapon systems, or crew hatches. Weight distribution had to maintain the Sherman's center of gravity within acceptable parameters. Most importantly, the welds had to be structurally sound enough to keep plates attached during combat maneuvering and weapon firing. Staff Sergeant Michael Torres, of the maintenance section, had worked as a structural welder in Chicago shipyards before the war. His experience with high-stress joints and quality control proved invaluable. Torres examined the German steel with professional interest, noting the material quality and hardening characteristics. The armor could be welded using standard equipment, he concluded, though the thick plates required careful heat management to prevent warping or stress fractures. The welding work began at 1900 hours, and continued through the night. Torres supervised every joint, ensuring proper penetration and structural integrity. Each section of German armor received reinforcement brackets to distribute stress loads across the Sherman's hull structure. The plates were positioned to create standoff distance from the factory armor, approximately 4 inches of air gap that would disrupt shaped charge jet formation if the tank encountered Panzerfaust weapons. By 0400 hours on December 7th, Rothery's Sherman carried 6 sections of salvaged German armor welded to its frontal hull and turret. The modification added approximately 700 pounds of weight to the vehicle's front end, within acceptable limits for the suspension and transmission systems. Most importantly, the added protection provided approximately 50 to 60 millimeters of additional armor thickness, potentially sufficient to defeat German 88mm rounds at typical combat ranges. Sooner than expected. On December 10th, 3rd Armored Division attacked German positions near Düren as part of the continuing offensive toward the Ruhr River. Rothery's platoon advanced through terrain that intelligence reports described as lightly defended. The assessment proved incorrect when concealed anti-tank guns opened fire at ranges below 600 meters. The German 88mm round struck Rothery's Sherman at 09:23 hours. The shell hit the improvised armor plate welded over the right side of the frontal glacis. The impact was tremendous, rocking the 33-ton vehicle and filling the crew compartment with smoke and concussion. But the German armor had absorbed most of the shell's kinetic energy. The projectile penetrated the salvaged plate, but lacked sufficient force to defeat the factory armor beneath. The crew compartment remained secure. The tank remained mobile. All 5 crew members survived without serious injury. Post-battle, inspection revealed the effectiveness of the modification. The German shell had completely penetrated the salvaged armor plate, but had been deflected slightly off its original trajectory. The factory Sherman armor showed impact deformation, but no penetration. Without the additional protection, the shell would certainly have breached the crew compartment with fatal results. Word of the successful modification spread rapidly through informal channels that connected tank crews across multiple divisions. Maintenance personnel discussed welding techniques and material sources during routine supply meetings. Crews compared armor configurations during brief rest periods. Officers who had witnessed the effectiveness of improvised protection became quietly supportive of modifications that regulations technically prohibited. By late December, the practice had evolved from isolated experiments into widespread unofficial policy. Tank crews throughout 1st and 3rd Armies were welding salvaged armor, track sections, and other materials to their Shermans in systematic efforts to improve survivability. The modifications varied based on available materials and crew ingenuity. Some installations were crude, barely attached reinforcements that provided minimal protection. Others represented sophisticated engineering efforts that distributed weight carefully and provided genuine ballistic improvement. The Ordnance Department response to this development revealed the tension between institutional procedure and combat necessity. Technical officers correctly noted that unauthorized modifications violated equipment specifications, added uncontrolled weight that stressed mechanical systems, and created maintenance complications. Field manuals specified exact procedures for armor repair and modification, none of which included welding salvaged enemy equipment to American tanks. Colonel James Harrison of 1st Army Ordnance Section filed official reports documenting the widespread violations of technical regulations. His memoranda detailed dozens of specific cases where crews had modified vehicles without authorization, creating what he termed field expedient alterations of unknown effectiveness and questionable structural integrity. The reports recommended immediate cessation of unauthorized modifications and disciplinary action against personnel who had violated equipment specifications. The recommendations were quietly ignored by field commanders who understood combat realities better than staff officers in rear area headquarters. General Omar Bradley's response to one such report was characteristically direct. If modifications improve crew survival without compromising mission capability, I'm not interested in stopping them. Focus on keeping tanks running, not on regulatory compliance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tension between official policy and battlefield practice reflected fundamental differences in institutional perspectives. Engineers thought in terms of specifications, testing procedures, and documented performance characteristics. Combat soldiers thought in terms of immediate threats and available solutions. The gap between these worldviews had existed throughout military history. What made the Sherman armor modification controversy unique was the scale and spontaneity of the field innovation. Technical analysis of the modifications revealed surprisingly consistent patterns. Most crews focused protection on frontal areas where German anti-tank fire was most likely to strike. The added armor typically measured between 4 and 8 inches of additional thickness, whether from salvaged plates, track sections, or other materials. Weight additions generally remained below 1,000 pounds, keeping suspension and transmission loads within marginal tolerance. More importantly, ballistic testing of captured, modified Shermans showed genuine protective improvements. Salvaged German armor plates could defeat or significantly degrade 88mm rounds at ranges beyond 500 meters. Track sections provided effective protection against shaped charge warheads by disrupting jet formation. Even sandbags and concrete, dismissed by some engineers as theatrical rather than functional, could cause premature detonation of time-fused high-explosive rounds. The statistical evidence emerged gradually from division casualty reports and vehicle loss analyses. 3rd Armored Division's records showed that Shermans with frontal armor modifications experienced approximately 42% fewer catastrophic kills compared to unmodified vehicles during comparable combat operations. The data suggested that improvised armor was saving approximately 35 crews per month within a single armored division. 1st Army intelligence officers compiled similar statistics across multiple units, finding consistent patterns. Modified Shermans showed reduced crew casualties, higher mission completion rates, and better survival probability during sustained combat operations. The modifications weren't perfect. Some installations failed under combat stress. Weight additions occasionally caused mechanical problems, but the overall trend was unambiguous. Additional armor meant additional survival. Lieutenant Colonel William Bailey of the Armored Force Board studied the phenomenon with professional interest. His background included MIT, mechanical engineering training, and 3 years of armor development at Aberdeen Proving Ground. The unauthorized field modifications represented everything that formal military engineering culture distrusted. No controlled testing, no documented specifications, no proper authorization. Yet the statistical results suggested remarkable effectiveness. Bailey's analysis focused on why improvised modifications succeeded despite violating standard engineering procedures. The answer involved combination of factors. Combat crews possessed direct knowledge of vulnerability patterns that test engineers lacked. Battlefield conditions provided immediate feedback about modification effectiveness. Most importantly, crews had personal incentive to develop genuinely protective solutions rather than theatrical gestures. The institutional lesson was potentially revolutionary. Perhaps complex engineering problems didn't always require centralized solutions developed through formal procedures. Perhaps battlefield experience and practical knowledge could generate innovations that laboratory testing might never discover. The implication challenged fundamental assumptions about military expertise and proper channels for technical development. Bailey's classified report to the Armored Force Board, dated January 15, 1945, recommended selective authorization of field armor modifications based on documented effectiveness and mechanical compatibility. The recommendations stopped short of endorsing wholesale regulatory abandonment, but acknowledged that combat experience had revealed protective solutions that peacetime testing had missed. The report's distribution was limited to senior officers in armor development and procurement offices. Public acknowledgement that field modifications exceeded factory protection in certain applications would create uncomfortable questions about original design specifications and institutional decision-making. The politics of admitting that enlisted tank crews had solved problems that engineers with advanced degrees had missed were simply too complicated. Meanwhile, in maintenance areas throughout the European theatre, the welding continued. Crews collected materials from destroyed German vehicles, cut plates to required dimensions, and installed armor without formal approval or official acknowledgement. The modifications represented practical, problem-solving by men whose lives depended on results rather than procedures. Rothery's Sherman received additional modifications throughout January and February 1945 as 3rd Armored Division fought toward the Rhine River. Each combat engagement provided feedback about vulnerable areas and effective protection. The turret received salvaged armor plates over ammunition storage areas. Track sections were welded to hull sides to counter Panzerfaust attacks from urban combat. The modifications accumulated weight and maintenance complications, but they also accumulated survival probability. By March 1945, Rothery's tank carried approximately 1,400 pounds of additional armor distributed across frontal, turret, and side surfaces. The modifications had required approximately 60 hours of welding work performed during maintenance periods and rest days. Total material cost was zero. Official approval remained non-existent. The result was a Sherman tank that had survived 7 direct hits from German anti-tank weapons and delivered its crew safely through 6 months of continuous combat operations. The human cost of the original armor inadequacy could be measured in the replacement crews that cycled through destroyed Shermans. 3rd Armored Division records documented 188 replacement drivers assigned to the division between June and December 1944. Of those, 93 were killed in action, and 61 were wounded severely enough to require evacuation. The casualty rate exceeded 50%, meaning that statistically, every driver position was filled by wounded or dead men approximately once every 6 months. The modifications didn't eliminate casualties. German 88mm guns at close range could defeat even heavily modified Shermans. Mines, artillery fire, and mechanical failures continued killing crews regardless of armor improvements. But the statistics showed measurable reduction in fatal penetrations from the frontal arc, which represented the most common direction of anti-tank fire during offensive operations. Staff Sergeant Michael Torres, whose welding expertise had enabled many of the modifications, kept informal records of installation work performed by 3rd Armored's maintenance section. Between December 1944 and March 1945, his crew had assisted with armor modifications on 73 Sherman tanks. The work consumed approximately 1,100 hours of labor, all performed during supposedly off-duty periods. None of it appeared in official maintenance logs. Torres understood the technical compromises involved in field modifications. The welding quality varied depending on available equipment and working conditions. Some installations used improper materials or inadequate reinforcement. Weight additions occasionally exceeded safe limits, causing premature transmission or suspension failure. But the alternative was sending crews into combat with armor protection that everyone knew was inadequate against standard German weapons. The ethical dimension troubled some officers who were caught between regulatory responsibility and crew survival obligations. Technical manuals existed for legitimate reasons. Uncontrolled modifications could create cascade failures that endangered crews more than inadequate armor. But refusing to authorize protective improvements meant accepting higher casualties from known vulnerabilities. The moral calculus provided no comfortable answers. Colonel William Harrison's final report on unauthorized modifications, submitted to Ordnance Department headquarters in April 1945, acknowledged the regulatory violations while documenting statistical effectiveness. His recommendations carefully avoided directly endorsing illegal modifications, but noted that prohibition had proven unenforceable and possibly counterproductive. The report suggested developing standardized modification kits that could be installed through proper channels, though everyone understood that such programs would require months of development while the war continued. The German surrender on May 8, 1945, rendered most of these debates academic. Tank crews stopped welding additional armor because combat operations had ended. Maintenance sections stopped installing modifications because replacement Shermans were no longer needed. The massive accumulation of battlefield experience and improvised solutions simply dissolved as units deactivated and personnel returned home. The statistical accounting began in occupied Germany during the summer of 1945. Ordnance Department analysts compiled comprehensive data from division maintenance records, attempting to quantify the effectiveness of unauthorized armor modifications. The work proceeded in requisitioned office buildings, where clerks typed reports on captured German typewriters while displaced persons camps filled the surrounding countryside. Captain Donald Mitchell of the Technical Intelligence Section supervised the analysis with methodical precision. His team examined maintenance logs from 6 armored divisions, correlating armor modification records with casualty reports and vehicle loss statistics. The data revealed patterns that formal testing had never anticipated. Sherman tanks carrying frontal armor modifications showed 47% reduction in catastrophic kills compared to unmodified vehicles during equivalent combat operations. The survival advantage appeared most pronounced in offensive operations, where German anti-tank guns engaged from prepared defensive positions. Modified tanks absorbed hits that would have been fatal to factory specification Shermans, allowing crews to survive long enough to withdraw or suppress enemy positions. The weight of added armor ranged from 400 to 1,800 pounds per vehicle, with median installations adding approximately 900 pounds. Mechanical reliability decreased slightly as weight increased, with transmission and suspension failures occurring approximately 12% more frequently in heavily modified tanks. But the trade-off proved favorable. Reduced combat losses more than offset increased mechanical attrition. Crew casualty statistics provided the most compelling evidence. Drivers in modified Shermans experienced 38% fewer fatal injuries compared to drivers in unmodified vehicles. The protection concentrated on frontal areas saved lives during the most common engagement geometry. German anti-tank fire typically struck advancing tanks from frontal or oblique angles, making frontal armor the most critical survival factor. Mitchell's preliminary report, dated July 23, 1945, documented these findings with careful statistical language. The tone remained clinical, avoiding any suggestion that unauthorized modifications had been necessary or that original armor specifications had been inadequate. But the numbers spoke clearly enough. Field improvisation had achieved protective improvements that factory design had not provided. The human cost appeared in different records. Casualty reports from 3rd Armored Division documented 1,217 tank crew deaths during 11 months of combat operations. Each notification carried a name, rank, and hometown. Each represented a family that would receive a telegram expressing the nation's gratitude for ultimate sacrifice. The statistics measured human tragedy in aggregates that made individual losses manageable for institutional accounting. Corporal James Rothery survived the war with his original crew intact, a statistical improbability that reflected both luck and improvised armor protection. His Sherman had absorbed 9 direct hits from German anti-tank weapons between December 1944, May 1945. 3 penetrations would certainly have been fatal without additional armor. The mathematics of survival had favored his crew because they had refused to accept factory specifications as adequate. The story could have ended there, with statistical confirmation that field modifications had saved measurable numbers of American lives. But the institutional implications extended beyond immediate combat effectiveness. The unauthorized armor improvements represented a fundamental challenge to military engineering, culture, and procurement processes. Lieutenant Colonel William Bailey's confidential analysis, prepared for the Armored Force Board in August 1945, examined these broader questions. Why had combat crews identified vulnerability patterns that testing engineers had missed? Why had field improvisation produced more effective solutions than formal development programs? The answers suggested uncomfortable truths about peacetime military institutions and their capacity for adaptation. Testing procedures at Aberdeen Proving Ground had evaluated Sherman armor against known German anti-tank weapons using standardized methodologies. The tests measured penetration resistance at specified ranges and impact angles, but combat conditions rarely matched test parameters. German guns fired from concealed positions at unexpected ranges. Crews encountered weapons that intelligence reports had not anticipated. The controlled environment of proving grounds could not replicate the chaotic reality of European battlefields. More significantly, testing engineers lacked the immediate feedback that combat crews experienced. When a test shot failed to penetrate armor plate, engineers recorded the result and moved to the next test sequence. When a combat hit failed to penetrate, 5 men remained alive to learn from the experience and adjust their protective measures accordingly. The motivation for accurate assessment differed fundamentally between laboratory and battlefield. Bailey's report recommended significant changes to armor development procedures, including mandatory field testing under combat conditions, direct consultation with experienced crews during design phases, and streamlined approval processes for field modifications that demonstrated statistical effectiveness. The recommendations challenged institutional assumptions about expertise and proper development channels. The political sensitivity of acknowledging that enlisted mechanics had solved problems that engineering officers had missed ensured that Bailey's report received extremely limited distribution. Only 7 copies were produced, each classified confidential and restricted to specific individuals in armor development offices. The document acknowledged effectiveness of unauthorized modifications, while carefully avoiding any suggestion that original procurement decisions had been inadequate. Meanwhile, in maintenance depots across occupied Europe, salvaged German armor was being collected for scrap metal recycling. The plates that had protected American tank crews were cut apart and loaded onto rail cars for shipment to steel mills. The improvised modifications were removed from surviving Shermans as units prepared vehicles for long-term storage or transfer to Allied nations. The physical evidence of field innovation was systematically erased as the military returned to peacetime procedures and standardized specifications. Rose Willow Monroe, the Willow Run riveter whose work had helped produce the B-24 Liberators, found herself unemployed by August 1945 as war production contracts were cancelled. The massive industrial mobilization that had sustained Allied operations was dismantling with remarkable speed. Tank production lines went silent, armor plate mills shut down, the economic machinery that had produced 33-ton Shermans at rate of hundreds per month simply stopped. The final accounting appeared in Army Ground Forces statistical summaries compiled during 1946. American armored forces had deployed approximately 20,000 Sherman tanks to the European theater between June 1944 and May 1945. Of these, 4,295 were destroyed by enemy action, and 3,127 sustained major combat damage. The replacement rate suggested that every deployed Sherman was statistically destroyed or severely damaged approximately 1.4 times during the 11-month campaign. Crew casualty statistics showed 6,837 tank crewmen killed in action in the European theater, with an additional 8,214 wounded seriously enough to require medical evacuation. The human cost of armored warfare appeared in these numbers, though the statistics provided no information about faces, families, or interrupted lives. The question of how many lives had been saved by unauthorized armor modifications could not be answered with precision. Mitchell's analysis suggested approximately 47% reduction in catastrophic kills for modified vehicles, but translating that percentage into specific numbers required assumptions about engagement, frequency, and hit probability that data could not support definitively. The conservative estimate suggested between 400 and 700 American tank crew lives preserved through field improvisation during the final 6 months of combat operations. 400 to 700 fathers who returned home to their children. 400 to 700 letters that were never written expressing the nation's regret. The mathematics of survival translated into human terms that statistical reports rarely captured. Each life preserved represented entire futures that would unfold because crews had refused to accept inadequate protection as inevitable. Technical Sergeant Michael Torres returned to Chicago in September 1945, resuming work in the shipyards where he had learned welding before the war. His hands that had welded armor to 73 Sherman tanks returned to joining steel plates for cargo vessels and industrial equipment. The skills were identical. The stakes were different. No one's survival depended on weld quality in peacetime fabrication work. Torres kept no records of his wartime welding beyond official maintenance logs that documented routine repairs. The armor modifications had never officially existed, which meant there was nothing official to remember. He occasionally encountered other veterans who had served in armored units, and conversations sometimes turned to the improvised protection that so many crews had installed. But these discussions remained private, shared only among men who had experienced the specific terror of riding into combat in inadequately armored vehicles. The institutional memory proved equally ephemeral. Post-war armor development programs incorporated some lessons from European combat experience, but the specific story of unauthorized field modifications received minimal attention in official histories. Ordnance Department publications discussed armor penetration statistics and weapon effectiveness without acknowledging that combat crews had independently developed protective improvements that formal engineering had not provided. The Korean War brought renewed attention to tank survivability when American armored forces again faced anti-tank weapons in combat. Sherman tanks, now aging veterans of previous campaigns, served alongside more modern designs. Some units discovered that field armor modifications remained necessary to counter contemporary threats. The welding began again, though institutional memory of European improvisations had largely faded. Each generation of combat crews had to rediscover solutions that previous generations had developed. Professor William Bailey, who had analyzed unauthorized modifications as Lieutenant Colonel Bailey during the war, spent his post-military career teaching mechanical engineering at Carnegie Institute of Technology. His classroom lectures occasionally referenced the Sherman armor controversy as case study in design iteration and field testing. The story illustrated how formal engineering procedures could miss practical solutions that users discovered through direct experience. Bailey's academic papers on engineering methodology, published during the 1950s, developed theoretical frameworks for incorporating user feedback into design processes. The work drew heavily on wartime observations about institutional barriers to field innovation and the value of practical knowledge versus formal expertise. His students learned that complex problems sometimes had simple solutions waiting to be discovered by people with appropriate motivation and direct experience. The broader lesson transcended specific technical applications. Organizations that valued rigid adherence to procedure over adaptation to reality would consistently underperform compared to institutions that could learn from field experience and incorporate practical innovations. Military bureaucracy had resisted unauthorized modifications because they violated proper channels and formal specifications. Combat crews had installed the modifications anyway because survival mattered more than regulatory compliance. Corporal James Rothery returned to Pennsylvania coal country, resuming work in the mines where he had learned mechanical skills before the war. His hands that had helped install armor on Sherman tanks returned to maintaining mining equipment deep underground. The problems were similar: keep machinery running using available materials and practical knowledge. The consequences were different. Equipment failure meant production delays rather than combat deaths. Rothery rarely discussed his wartime service, though he maintained contact with his former tank crew through occasional letters and rare reunions. The 5 men who had shared 33 tons of steel through 6 months of combat operations had formed bonds that peacetime relationships could not replicate. They had survived together through combination of skill, luck, and improvised armor that regulations had never authorized. The salvaged German armor plate that had saved Rothery's life had been removed from his Sherman during unit deactivation in Germany. The tank itself was probably scrapped or transferred to another nation's military. The physical evidence of his survival had vanished into the massive demobilization that transformed wartime armies back into peacetime organizations. Only the memories remained, and memories faded faster than most veterans expected. By 1960, 15 years after the war's end, the specific story of Sherman armor modifications had largely disappeared from institutional memory. New generations of officers studied armor development without learning about the field innovations that had saved hundreds of crew lives. Ordnance Department histories discussed Sherman tank operations without acknowledging that combat units had systematically violated equipment specifications to improve survival probability. The erasure was neither conspiratorial nor deliberate. Military organizations simply moved forward, focusing on current challenges rather than documenting past controversies. The uncomfortable questions about why formal engineering had missed vulnerabilities that combat crews immediately recognized were easier to ignore than to examine. Institutional culture preferred celebrating official innovations over acknowledging unauthorized improvisations. The statistical evidence survived in archived maintenance reports and casualty records, though few researchers examined these documents systematically. The numbers remained clear for anyone who sought them. Modified Sherman, tanks showed significantly better crew survival rates than unmodified vehicles during comparable combat operations. Field improvisation had achieved measurable protective improvements using salvaged materials and crew initiative. The human stories proved more difficult to preserve. Individual veterans carried memories of specific incidents where additional armor had meant the difference between survival and death. But these personal recollections scattered as veterans aged and died, leaving only aggregate statistics in archived files that few people consulted. Michael Torres died in 1973, his obituary noting service with 3rd Armored Division, but providing no details about the 73 tanks his Welding had helped protect. William Bailey died in 1981, his academic legacy including theoretical frameworks for engineering methodology, but no popular recognition of his wartime analysis of field modifications. James Rothery died in 1994. Taking with him direct memory of the moment salvaged German armor had deflected an 88mm shell that would otherwise have killed his crew. The statistical reports remained in archives at the National Archives and Records Administration, available to researchers who knew where to look and what questions to ask. Captain Mitchell's analysis from July 1945 documented the 47% reduction in catastrophic kills for modified Sherman tanks. Lieutenant Colonel Bailey's confidential report from August 1945 explained why field improvisation had succeeded, where formal engineering had not anticipated the problem. The numbers told a story that institutional memory had largely forgotten. Contemporary armor development incorporates lessons that previous generations learned through bitter experience. Modern military vehicles undergo field testing under combat conditions. Design teams consult extensively with experienced crews. Modification approval processes allow faster implementation of protective improvements discovered through operational experience. These procedures represent institutional learning from episodes like the Sherman armor controversy, though the specific historical precedents are rarely acknowledged. The fundamental tension between regulatory control and field adaptation remains unresolved. Military organizations require standardization and formal procedures to maintain operational effectiveness across large formations. But combat conditions generate unique problems that centralized planning cannot always anticipate. The balance between these competing requirements shifts continuously, as institutions learn from each generation's experience and then gradually forget those lessons as personnel rotate and institutional priorities change. The Sherman armor modification story illustrates several persistent patterns in military innovation. First, combat personnel possess direct knowledge of operational vulnerabilities that staff officers and testing engineers may not recognize. Second, bureaucratic resistance to unauthorized changes often reflects institutional priorities rather than technical judgment. Third, statistical analysis of field experience can reveal effectiveness of improvised solutions that formal testing might never evaluate. Fourth, institutional memory proves remarkably short when lessons challenge established procedures or suggest that official specifications were inadequate. These patterns transcend specific technical contexts. They appear in discussions of infantry tactics, aircraft design, logistics procedures, and countless other military domains where field experience generates insights that formal doctrine has not captured. Organizations that can systematically learn from field innovation while maintaining necessary standardization gain significant advantages over institutions that rigidly enforce procedure regardless of operational feedback. The mathematical precision of survival statistics provided the clearest measure of field modification effectiveness. 47% reduction in catastrophic kills meant hundreds of American tank crew members returned home to families rather than being buried in European military cemeteries. The statistic represented aggregated human futures: children who grew up with fathers present, marriages that continued, careers that unfolded over decades, rather than ending in German forests during winter 1944. 400 to 700 lives, according to conservative estimates from incomplete data. The actual number might have been higher. Statistical analysis could not capture every incident where additional armor deflected a shell that factory specifications would not have stopped. The informal nature of modifications meant many installations went unrecorded in official documents. The true impact remained unknowable with precision, but clearly significant in scope. The cost of these modifications appeared primarily in maintenance complications and mechanical wear, rather than financial expenditure. The salvaged German armour cost nothing except labour to cut and install. The welding consumed standard supplies already available in maintenance sections. The primary expense was crew time spent installing protection rather than resting between combat operations. Men welded armour during hours they could have slept because survival outweighed exhaustion. The institutional cost appeared in challenged assumptions about expertise and proper development channels. If enlisted mechanics could solve armour protection problems that engineering officers had missed, what did that suggest about the distribution of technical knowledge within military organizations? If field modifications proved more effective than factory specifications, what did that imply about formal testing procedures and procurement decisions? These questions threatened established hierarchies and professional identities in ways that accurate answers could not easily resolve. The erasure of this story from institutional memory represented one way to manage these uncomfortable questions. By treating field modifications as temporary expedients rather than systematic innovations, official histories avoided acknowledging that formal processes had failed to provide adequate protection. By emphasizing regulatory violations rather than statistical effectiveness, technical reports maintained the primacy of proper channels over practical results. The narrative that survived stressed order and procedure rather than adaptation and survival. Yet the statistics remained, buried in archived maintenance reports and casualty records. Future researchers examining these documents could reconstruct the story of how American tank crews had systematically violated equipment specifications to improve survival probability. The numbers documented both the extent of field modifications and their measurable effectiveness. The evidence existed for anyone willing to examine it. The lesson transcended military history. Organizations facing rapid adaptation requirements often discover that field personnel possess practical knowledge that formal expertise has not captured. Rigid adherence to established procedures may produce inferior results compared to controlled experimentation with user-generated innovations. Statistical analysis of operational experience can reveal effectiveness patterns that laboratory testing misses. Institutional memory proves remarkably selective when preserving lessons that challenge established practices. Abraham Wald, the statistician whose analysis of bomber damage patterns had revolutionized aircraft survivability during the same war, understood these dynamics from different contexts. His framework for examining survivorship bias, learning from what was not observed, rather than what was applied equally to tank armor analysis. The Shermans that returned with armor damage showed where protection was adequate. The Shermans that never returned revealed where protection had failed. Field crews understood this intuitively and modified their vehicles accordingly. The parallel between Wald's bomber armor analysis and unauthorized Sherman modifications extended beyond statistical methodology. Both cases illustrated how formal expertise could miss critical patterns that direct experience revealed. Both demonstrated that institutional resistance to counterintuitive solutions often reflected bureaucratic priorities rather than technical judgment. Both proved that statistical rigor applied to operational data could validate field innovations that regulations had prohibited. The mathematical precision of survival analysis provided powerful tools for evaluating improvised solutions. But the human judgment to recognize which problems required solving and the practical knowledge to develop effective solutions using available materials came from combat crews rather than staff officers. The combination of field innovation and statistical validation produced better results than either approach could achieve independently. By 1995, 50 years after the war's end, almost all combat veterans who had installed or benefited from armor modifications had died. The direct memory of why crews had violated regulations and how improvised protection had saved lives passed into history. Surviving documentation provided statistical evidence but could not capture the immediate terror that had motivated field improvisation or the relief crews felt when additional armor stopped shells that factory specifications would not have defeated. The institutional knowledge had also largely disappeared. Current armor development officers studied modern threats and contemporary materials science without examining historical precedents for field modification programs. The specific lessons about institutional resistance to unauthorized innovation and the effectiveness of user-generated solutions had to be relearned through each generation's experience, rather than systematically transmitted through doctrinal education. The physical evidence had vanished entirely. Surviving Sherman tanks in museums and private collections had been restored to factory specifications, their improvised armor modifications removed as non-original alterations. The salvaged German plates that had protected American crews were long since recycled into peacetime steel production. The welded brackets and reinforcement structures had been cut away during vehicle preservation. Nothing remained except archived photographs showing additional armor that restoration efforts had erased. Yet the pattern persisted across subsequent conflicts. American armored vehicles in Vietnam, Iraq, and Afghanistan underwent similar field modification programs, as crews discovered vulnerability patterns that peacetime testing had not identified. Each generation welded additional armor, installed improvised protection, and violated equipment specifications in efforts to improve survival probability. Each generation's modifications provoked similar institutional resistance based on regulatory compliance rather than operational effectiveness. The recurring pattern suggested that organizations had not learned the fundamental lesson. Field personnel will adapt equipment to meet operational requirements regardless of bureaucratic resistance. Statistical analysis of field experience provides valid evidence about modification effectiveness. Institutional memory proves inadequate for transmitting practical lessons across generational transitions. The same conflicts between regulation and adaptation played out repeatedly because organizations could not maintain corporate knowledge about previous iterations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.